Hi there. Welcome to Computing Foundations. This is a channel focused on helping beginners learn the foundational concepts of computers, programming, and the math, science, and art of electrical computation. I'm Josh. I'm a retired software engineer. I worked for about 20 years designing and writing software, and I find the foundational concepts of computing fascinating. My goal is to help you appreciate this world-changing field of knowledge. Today, we're talking about constants. And this is a follow-up from our video on variables. And let's break this down in a really simple way. If variables are just a named area of memory that you can alter during your programming, constants are kind of the opposite, or the nemesis of the variable. These are unchanging areas of memory. They won't change during the execution of your program. Let's compare and contrast the differences between variables and constants. Both of them have names, often. They can be named. Both of them are typed. They have a certain type that they get stored as in memory, either an integer, a floating point, a character, etc. And lastly, changeability. Variables, you can change them during your program and reassign them to different values. Constants never change. So let's take a few examples. You've already seen examples like this in some of the programs we've looked at. So here I'm defining a variable called age, and I'm assigning it to the value 45. That is called a constant. Specifically, it's called a literal constant. What I want you to be aware of is that the way that I've written this is important. There's no decimal place. So integer constants can only be specified as numbers and optionally a negative sign at the beginning if you want. So as an option, I could say negative 45. Next, floating point constants. Here I'm naming a floating point variable called cost, and I'm assigning the value 19.99. This is going to be a constant in memory, and it will be stored as a floating point value because I put a decimal place there. If you don't put the decimal place, it will not be stored as a floating point value. The last kind of constant that we've seen is a character constant. Here I'm defining a character variable called initial, and the way you write a character constant is you place it inside of single quotation marks, the character that you want, closing the quotation, and that's how you specify a character in memory. Now I say these have types because they're actually going to be stored in memory, even though you only use them one time. A space in memory that has the size of an integer, normally 4 bytes, will be reserved for storing this number during your program. The same happens here, but it'll be stored as a double in memory, meaning it'll take up 8 bytes. This will be stored as a character, so it's only going to take up 1 byte in the memory of your program. Now, we have some options on how we specify integers as variables. This can be useful in programs sometimes. Rather than specifying a value as a decimal value in the base 10 number system, sometimes you want to specify a value as binary. And here's an example of how you do that. You begin your number with 0, then the letter B, and then a sequence of 1s and 0s. This sequence of 1s and 0s happens to be equal to 45. So by setting age to this binary number, I'm doing the same thing as happens in this statement where I set it to 45. The other way I can set an integer is to use hexadecimal notation. We haven't talked about hexadecimal yet, so let me give you a quick overview. Hexadecimal is another number system that can be used in the world. It uses 16 symbols, 0 through 9, and then the symbols A through F. One reason hexadecimal shows up in computing is because it's a really nice way to specify the value of 4 bits. So look at this. The binary value 0000 is hex 0. the binary value 0001 is hex 1. And we continue through the basic base 10 number system until we get to this particular value, 1010, which is 10. We represent that in hexadecimal as an A. So instead of writing a 10, instead of writing two symbols, you just write one symbol, an A, and that represents 10, and this is the binary for that. All the way up to 11111, the largest binary value that I can store in 4 bits, and hex specifies that as F. So sometimes this can be a simpler way to specify a value in binary, or to specify a number that you're thinking about in terms of binary. So for instance, 45 is 2D. Okay? To make sense of that, you'll have to go do the math and see how that conversion works by multiplying the numbers out correctly. We're not going to go over that today. But hexadecimal is another way you can specify an integer. You probably won't look at that a lot in your early days of programming, but it's possible. Now, a few other concepts. Let me walk you through how floating point numbers can be specified. You've already seen the most straightforward way to specify a floating point, and that's just writing a decimal number with a decimal point and numbers after the decimal point. Optionally, you can write them in scientific notation. This example here is synonymous with saying 1.999 times 10 to the first power. So to specify a scientific notation, you do the fractional part, then a e, and then the exponential part of the number. So this ends up being in memory 19.99, the same value we set earlier in the example. It's just another way to specify it. Another example here showing you with a negative exponent, you can specify a really small number, 1.3 times 10 to the negative 10. This is the value that would be stored in the floating point. So it's basically 9 zeros after the decimal place, followed by 1999. Just another way to specify a number. Now, a final concept concerning constants. A lot of times you will just write literal constants in your software by writing a number. But often we want to define our constants ahead of time using what's called a directive to the compiler. So at the top of any C file, you can write a statement like this: pound define, then a symbol name, then a value. This can be an integer, it can be a floating point number, it can be a character. And later in the program, we can reference this number by just typing in this symbol that we wrote in the definition. So here's an example. I define a floating point variable called total, and I set it equal to price, which was earlier set to be $19.99, plus the price times the sales tax. What's nice about this is it's really easy to read this code. I understand what you're doing because you've used a named constant that has some meaning to the reader. Oh, you're multiplying the price by a sales tax. That's why we sometimes use constants instead of just writing the number into the software. The other benefit of using a constant is, take as an example pi, 3.14. Imagine I have a program where I'm calculating the area of lots of different objects, lots of different circles, but then later I want to change the value of pi to use more significant digits to have a more accurate value for pi. If I don't use a named constant, I'll have to go back into my code and change every single place where I wrote 3.14. It's inefficient and it's error prone. If I just use a constant and refer to the constant pi in my code, I can come back and change the value of it in just one place. We're going to see this a lot as we move forward, that it's often just smarter programming to use a constant. It makes it easier to maintain and update your code in the future. So the reasons for constants: easier to read, and you can change the value in just one place instead of having to go through your code and fix everything. So that's our brief overview of constants. It's a pretty simple concept, but something that you're going to see in our programs as we go forward. Thanks for listening.